We have introduced TSP and VRP in discrete models. So from today, we will further extend the model for TSP and VRP to even larger scale, or to some extent in the continuous model. So first, we will provide some terminologies and definitions for TSP and VRP on surface. So previously, when we have all the input for TSP or VRP, we give you the adjacent matrix distance, which indicates the distance from node I to node J. This setting is definitely perfect for discrete modeling. And then in our Colab, we have also introduced a way we generate the point, where we provide you with the location. For example, for xi, we indicate xi1 and xi2, which give you the location of node I. And then the distance from node I to node J, we can define it based on some norm, which is our Cij. So here in our previous examples, we use two norms. Then this gives us the square root version. We can have other versions for the norm to calculate the distance. So in general, we typically consider a continuous case where we have a surface. For example, we call this shape A, and then the area of this shape is defined by coordinate of this set, or we just simply define it by big letter A. And then for this continuous space, if we have 2 points ij, we can define somewhat a norm. This norm can have several possible ways, like one norm. One norm just means so the one norm is typically used to describe the distance when we traveled in urban area where the roads are built in grids. So you need to travel from one point to another point by going through the road network. For example, if this is I, this is J, then you need to travel this way from I to J. Hence, you will have the distance as the one norm describes the difference of the two coordinates and then add them up. And also, we can have our two norm, which we already introduced. Some special cases, we may even consider infinity norms. So that just consider the maximum value of two coordinates. Okay, so let's consider example when we have different norms, right? Let's see, we have P indicates the norm, and then P can be equals to 1, P can be 2, and then P can be infinity. So if we try to draw the equal norm contour, then we can observe some interesting phenomena. For example, let's see if we have, let's take an example for P equals to 1 first. And then in this case, if we assume xj is the origin and xi minus xj, let's see the distance from I to j is considered to be 1. And then in this one norm cases, we can draw a contour of xi. Yeah, so actually this is a square. Then if we have xi minus xj is smaller than 1, then that will give you all the inner part of this shape. So similarly, we can have two norm. Then if our xj is the origin, then this can give us a circle. So if we have this inner part smaller than 1, this gives us all the points inside this circle. And then for infinity norm, so this gives us also a square, but this square is bounded by 1. So if we have smaller equals to 1, this gives us a smaller area here. So if we combine all these three measures together, the one norm is the smallest area. So this is one norm. And then the two norm is the circle. So this gives us circle. And then the infinity norm outside. Okay, so this shows what is a boundary when x p norm equals to 1. This can help you understand the concept of p-norm when p equals to 1, 2, and infinity. So based on the application context, we may choose p equals to 1, p equals to 2, or p equals to infinity, and to estimate our travel cost from I to j. Now let's try to consider how can we estimate TSP distance for continuous space. So first, problem is given by some boundary. Let's see if we have the market area, which indicates by set A, and then there will be a lot of customers distributed in this area, maybe randomly distributed, satisfy certain distribution. And then our goal is to find out if there's a way we can estimate an TSP for. So let's define L to be the total travel distance. And then definitely this TSP distance determined by the customers. Let's see N, number of customers. And also it may relate to the market area. That's A to be the coordinate of the market area A, which is the size of area. So our goal is to estimate the TSP distance given the number of customers and a certain size of the area. So this is a hard task. You can see the number of customers is only a macroscopic measure. The distribution of customers' location can be very different in different problems. So we will just consider an aggregated measure. That means when we have different customer distributions. So in expectation, what is the travel distance for a TSP? So in this case, the number of customers is given, and then we may sample customers in our market area. For example, in our previous Colab cases, we sample the customers based on a uniform distribution from 0 to 1. Let's see, we have the location of the customer satisfy a uniform distribution, and then we sample n customers. Let's see, n equals to 10, and then this will give us the customer will be distributed over a unit square and then may satisfy a uniform distribution in it. And then our TSP tour, the distance is L. So definitely for the unit square, the area is 1. So this gives us a simple illustration. So our goal is to find if there's a way we can estimate our TSP distance based on the number of customers and then the size of the area. So this seems a very interesting task. That's why we introduce a dimensional analysis first. So here we will try to apply the knowledge from dimensional analysis to give us some hint. So remember, in dimensional analysis, we want to first identify what is the variables for the physical system. So in our specific case for TSP, we want to estimate the distance, TSP distance, which is L. And then let's assume the unit, which is mile. And then we also have the area of the market, the size of the market area. So let's assume the unit is also in miles. So that will be mile square. And definitely we can consider the third parameter, which is the number of customers, and then there's no unit for the number of customers. Based on the knowledge in our previous course, we can create a matrix. We only have one unit, so this is a 3 by 1 matrix. And then for L, the unit is 1, area unit is square, the number of customers, the unit is 0. So we use our method introduced in the previous course. We want to solve the dimension matrix. So this gave us solution as A1 plus 2, A2 equals to 0. Because it has nothing to do with A3, and then here the rank of our dimension matrix equals to 1, and we have 3 variables, so we will have 2 unitless parameters. So we can pick up one is 0, 0, 1, and it indicates that A3 is 1 dimension. And then from A1 plus 2A2 equals to 0, we can have A1 is 1 and A2 is minus a half and then 0. So we created 2 unitless parameters. The first one actually will be the third parameter n, and then another unitless parameter is LA, the power of minus half. Then by our pi theorem, we can immediately get here's the equation, and then we simply organize it, can get f pi 1 equals to pi 2, and then this gives us. Okay, so if we want to estimate the average TSP distance from the market area and then the number of customers, it has to be in the form which is proportional to the square root of a and also multiply by a function over n. This is our pi theorem. So here we use our Colab to generate samples where we fix A to be 100, which is a market area is a 10 by 10 area. And then we generate the number of customers from 10 customers to 200 customers. And then we can draw as the number of customer increases. Here is 10 customers, here is 200 customers. We can see the TSP distance have this trend. And then this trend indicates some information for Fn. This is the number of customers. This is our TSP distance. And also we vary the market size from 0 to R here. So the area should be R squared. You can see as R increases from 1 to 20, then the TSP distance kind of linearly increases. So this tells us L equals to square root of A, which is, this is R, right? R equals to 1 to 20, right? So that indicates L is proportional to R, which is the square root of A, and also time a function of n, and then the shape of Fn looks like this curve. And our intuition can tell us this is somewhat square root. So we will guess L equals to square root A times some square root of n multiplied by some factor. Let's see, k. Okay, so let's try to prove from our observation we can guess the TSP distance is some constant times square root of service size A and then the number of customers. So in fact here our literature shows that for L1 metric, which means the distance is a summation of absolute value error. So when our space is given in L1 space, so the distance is 1 norm, and then this k value is around 0.92. And then if it is a Euclidean space, so your distance is the 2 norm or Euclidean norm, and then this k value will be around a little bit smaller, 0.72. Okay, so let's show why we can have this result. So we assume that the shape of the market area is just a square. We will discuss the shape, the impact of the shape later. So if the shape is a square, we can first try to decompose the big area into smaller area, which is also square. For example, here, let's see the number of squares on one side is equals to 2. So in this case, we divide the entire market area A into 4 sub-area. So this is A1, A2, A3, A4. So we want to estimate the total TSP distance on the big area A. So let's assume we already obtained the TSP tour for small areas A1 to A4. This is already the optimum TSP tour. So that means we can try to create a feasible TSP tour by connecting small TSP tour within each sub-area. For example, here we can connect A1 and A2 by break 2 points and add 1 additional link, break 2 points and then add additional link. So similarly, we can do this for all area across. By break the point within each TSP tour within sub-areas, we can connect a feasible TSP tour in the entire market area. So that means after we create this tour, the total distance here, we can see we have 4 TSP tour plus 4 connections. And then this is a feasible TSP tour for the big area. And then this is definitely greater or equal to the optimum TSP tour in this area. In general, when m is not 2, we can see m squared plus m squared will be greater or equal to the TSP tour for the whole area. And then as we already shown that this TSP tour within the sub area, we can try to approximate it based on in a small area. Here we can have n here. Okay, so in the sub area, the TSP tour will have a smaller area divided by square, and then the number of customers are also divided by square. And also the connection, we can easily show that the total distance for this connection will be smaller or equal to 6m square of a. Yeah, so this is relatively intuitive. For example, if we connect TSP tour between two adjacent blocks, the maximum distance for this connection will be this long. And then this distance is definitely smaller or equal to, this is 1 unit, 2 unit, 3 unit, which is 1 length, right? So this is greater or equal to 3 units. And then the return curve is also less than 3 units. So the connection of these two subtour will be less than 6 times the edge length, and then the edge length, which is square root of a divided by m. Distance for connecting two subtours will be smaller or equal to 6 times the edge length. The edge length is square root of a divided by m. So we have this term, and then we have a general TSP tour. So this gave us a upper bound of the TSP distance with respect to the market area A and the number of customers. Now let's continue our proof. So similarly, we can decompose the big area into smaller areas, similarly as A1, A2, A3, A4. But now let's assume that we have big TSP tour. This is already the optimum TSP tour. And then we want to create TSP tour within each sub area. So for example, we take out one area in A1, then this is our TSP tour, part of the TSP tour for the entire area. And then we can create a small TSP tour within this area. And then this TSP tour is a feasible TSP tour within this sub area. So you can see this is a feasible in A1. And then this feasible tour, two parts. One is a part of the original, the big TSP tour, and also we plus some added edges to create the subtour within this area. And we can easily show that this is smaller than the 4 edges. So this gives us a feasible TSP tour, so that will be greater or equal to the optimum TSP tour. The optimum TSP tour is given by the same expression, where we have smaller area and then the smaller number of customers. So this is only for one sub area, so we can add all the area together on the left hand side and then on the right hand side. So there will be m square sub areas. So on the left hand side, this will be the entire TSP tour, and then the second term will have m square times 4, and then this is greater or equal to m square sub TSP tour. So this one we have a lower bound estimation for our TSP tour of the entire area. So we connect these two expressions together. Okay, and then if we plug in the form, we replace this on both sides, we can get, so this one, the first term is cancelled, and then this one is the same, and then we can further cancel all the square root of a. So we will first show that as the number of customer increases, the estimation of the distance goes to infinity. So here, let's assume this is a unit square. Minimum TSP tour will be Fn. We need to prove that the distance goes to infinity as the number of customers sampled in this unit square goes to infinity. So first, let's assume the nearest point to I is j of I. So our TSP tour equals to summation of xij This is for the tour. And then this will be greater or equal to the distance to the nearest one. This makes sense because in a TSP tour, you may not travel always to the nearest point. Every time you travel to the nearest point, this is a myopic decision and may not be a TSP tour. So this is around, we have n nodes, and then for each node, if we calculate the nearest distance to its adjacent node, that gives us expectation of nodes to its nearest one. Without loss of generality, we can consider this as a first point. Yeah, for example, if we have 4 points, 1, 2, 3, 4, the TSP tour will be 1, 2, 2, 3, 3, 4, 4, 1. But actually the nearest distance from 1 is from 1 to 3. So nearest point to node 1 actually is 3. So if we add the distance together, 1, 3, 2, 3, maybe 3, 4, and also the nearest distance to 4 maybe 4, 3. So we can see 1, 3 is definitely smaller or equal to 1, 2, and then 4, 3 is smaller or equal to 4, 1. So the bar 1, this is a TSP distance. This is not. But this one gave us an expectation of the nearest distance. So 1, 3, 2, 3, 3, 4, 4, 3. This is can be considered as a random number, which is a distance from a point to the nearest one. Okay, so let's see why this distance goes to infinity. So suppose we have one point, and then we draw a circle with radius r. So if we sample a point, then the distance from I to j, let's see, we sample another point j, because j is sampled within the unit square. So if we sample another node j, then the probability that j lies in the neighborhood of I, the probability of j is in neighborhood of I actually will be pi r squared divided by 1, which is pi r squared. So in other words, the probability that, this is an illustration example in 2 norm, which is, we can generalize it into any other norms. And then because we have a lot of points, besides point I, we have n-1 points. For each point, there's a chance pi r squared that this dot will lie in this neighborhood. So we can see the probability that no points in the neighborhood. So that means for all j, this is outside R. So this equals to, because we generate a point independently, this is equal to, for each j, the distance is greater than R. We guarantee this happen, and then it happens -1 times. So on the other hand, if there are 1 point inside the neighborhood, then this will be the contrary of that. All dots are outside. And then this is equals to summation. And then we use Taylor expansion, and then we can easily prove that this one is smaller or equal to n-1 times the probability. So this is pi r squared. And this is smaller or equal to n pi r squared. So we choose a specific value that r equals to, then we can obtain the probability that some nodes is in this neighborhood is smaller or equal to a half. So we can have the expectation for the I to the nearest node, j. So because the first case r1 is greater than 0, the second case r2 is greater than r, so that we can get the expectation from I to its nearest node, gi should be greater or equal to r divided by 2. So this is this value. Hence we can have our minimum TSP toward is greater or equal to n times the expectation I to its nearest node, and then this is greater or equal to, and then this is goes to infinity as n goes to infinity. So previously we have shown that Fn is bounded by upper bound and the lower bound. As we can see that when n goes to infinity, Fn goes to infinity, so this constant term will not affect our result too much. So that tells us when n goes to infinity, we have around Fn divided by m squared. Because n is sufficiently large and m is always based on our decision, so we can choose m equals to square root of n, then we can approximately have times f1, and f1 actually is a k. So in this case, we have proved that this is for when our market area is a square. So in fact, when the market size, when the market area is not a square, we can similarly do this decomposition. So for an arbitrary shape, as long as the number of n is big enough, we can cut the irregular areas into smaller areas, where each of these areas are approximately a square. So we can apply similar analysis. And finally, we can show for any shape, as long as the shape is not too narrow, we can always obtain the minimum TSP tour given the size A and then the number of customers will always be estimated. And then when n goes to infinity, this will be equal.